Okay, so exercise 5. Now here we have to prove, and in fact this was mentioned when we were going through this part in the text, that the radius of any graph is less than or equal to its diameter, which itself is less than or equal to 2 times the radius. So let's see how this can be proved. Let G be a graph. The first inequality is almost immediate, since diameter of G is the largest possible distance between two vertices of G So that's why we have this. Because the radius of G, whatever it is after all a distance between two vertices of G, and this is an upper bound for any distance between, the distance between any two vertices of G has this as an upper bound, so naturally you have this inequality. Now for the other inequality, choose a central vertex. Say, we can name it anything, say V in G, and let X and Y be vertices in G such that the diameter of G is equal to the distance between X and Y. Now, you may of course want to write V belonging to not G but V of G. Precisely, that's what we should write, because V of G is the vertex set of G. But we have already agreed to somewhat relax the notation by using this kind of things, and from the context it's understood that these objects X, Y and V are actually vertices. Here we have of course mentioned the word vertex, but here X and Y are vertices. That's because we are measuring the distance between them, and anyway from the context it's understood that X and Y are vertices in G and not edges. But if you just simply write X and Y in G without saying anything else, then it will be confusing. Okay, but here there is no problem. Alright, now, well, of course a central vertex will exist, and the diameter of G will after all be the distance between some two vertices which are the farthest apart in the graph. There may be multiple such pairs of vertices, so we can choose any such pair. Now, this occurs by the triangle inequality, since D after all is a metric on the set of vertices of the graph. We have this less than or equal to the distance between X and V plus the distance between V and Y. Okay. Now, because we have chosen V to be a central vertex, right? So the radius of V, the radius of G will be equal to the distance between V and some other vertex. Say that other vertex is W. and W is a vertex in the graph such that this distance is the maximum. By the definition of radius, this is the maximum among all such distances. As you vary W prime over G means over the vertex set of G. So that means that if we replace each of these distances with this, that means we are likely writing more because it's the maximum among all such distances. You can take x in place of W prime here, so this is greater than or equal to this. At the same time, you can also take y in place of W prime here. This is again then greater than or equal to this. So that's why this sum is less than or equal to this plus y. Okay, so v comma w, where we of course have to now write where W is a vertex in G such that the distance between V and W is the radius of G. But then our diameter, we have proven that the diameter of G is less than or equal to 2 times this value. Which is equal to 2 times the radius of G. So that's how we have substantiated, we have established the second inequality also. So that completes the solution. Now let's see the next one. Exercise 6. I am not going to solve exercise 6 fully. Actually, there are 2 cases. I will solve one case and leave the other case to you. So let's first see what the exercise is. We need to recall a few things from the text in order to understand the exercise and then in order to solve it. Prove the weakening of this result of theorem one, 3, 4. Obtained by replacing average degree with minimum degree. Yes. Average with minimum degree. Deduce that the order of G is greater than or equal to this quantity for every graph G as given in that theorem. Okay, so now we need to first of all recall this quantity, the definition of this quantity, and then we need to recall the statement of this theorem. So let's do those things. So we are not going to write the solution immediately. We first do these things and then we will start the solution. Alright, so let's go back to when we were discussing these things, radius, diameter, all these things. Let D be a real number, any real number, and let G be a natural number, and remember that the set of natural numbers has 0 in it. Okay, so we are following that convention. In some texts, the natural numbers do not include 0. In some texts, it includes 0. It does not matter. This is not a discrepancy. It's just a matter of what you are calling natural and what you are not calling. Some people call 0 natural, some people don't call 0 natural. It's just that. You have to just simply make sure that whenever you are reading a text, in the beginning of the text, you make sure what the meaning of n is. In our n, 0 is there. Okay. Now, since G is a natural number, it's going to be either even or odd. We already know these things. Now, what we are going to do, we are going to define a quantity n naught depending on this D and G by this formula. N naught of D comma G is defined to be equal to this. Where we will say what R is if our G turns out to be an odd natural number, and as such it's of the form 2R plus 1 for some non-negative integer, that means again for some natural number R. So this R that you see here is actually nothing but G minus 1 over 2, G minus 1 divided by 2. So if G is of this form, then the value of this is, say, this. That is one case. And when G is even, then the value is defined to be this. And here R is G over 2. There is no need to separately write that this is odd, because from the form itself we can see that that is the case. So this is the definition of these quantities. And the quantity, let's just again see what this whole thing is for once. D is any real number and G is a natural number. To be more precise, G is a non-negative integer. If G is odd, then n naught of D comma G is by definition this, where R is G minus 1 over 2. And if G is even, then this quantity is defined to be this, where R is G over 2. Okay, now we state this theorem. This theorem, you go back to this part, you will see that it's by Allen, Hurray and Lineal. So the names of the authors. who came up with this theorem, and it came out in 2002. Okay, also all these things are already there. So now the thing is this. The statement of the theorem is this. I need not, of course, write everything. So here G is a graph such that the average degree of G is greater than or equal to some D which is greater than or equal to 2. That is given. What else is given is that the girth of G is greater than or equal to some G. It cannot be less than G, and this G of course is a natural number. If these conditions are given, then the order of G, the number of vertices in G should be at least n naught of D, G. So in order to state this thing, this bound, we have the definition. And the text does not have a proof of this. Likely it's an involved proof, but the author did mention after stating this theorem that a similar result is true if we can replace this average degree by minimum degree, and that we have been asked to prove here. See, prove the weakening. So we are weakening by replacing this average degree D by the minimum degree. Theorem 134 obtained by replacing the average degree with the minimum degree. And then of course we have to deduce this thing. So deducing this part also I will leave to you. It will be likely very easy. I haven't seen how this can be deduced, but I leave that part to you. And now we are going to prove not this theorem, but the theorem where you replace the average degree by the minimum degree of the graph, and which we are say calling delta. Everything else is same. Then you prove that the number of vertices in the graph is at least this, with the meaning of n naught of delta G defined by this thing. So let's see how this can be done. And I said that I will prove only one case. Two cases are there depending on the parity of G, namely when G is odd and G is even. So I won't do the even case, I will leave that to you. You can see the odd case solution part and proceed similarly. There will of course be differences, so you have to figure that out. Let's see if you can get it. And the proof in fact is similar to another result. You go to the text and you will see that before the definition of these quantities, there is a result which gives us an upper bound for the order of G. Here we are seeing a lower bound, there we have an upper bound in terms of girth and something else I can't remember exactly. So the ingredients will be similar and the approach will also be similar, but in the other direction. There we had an upper bound, so we had to do something. Here we will do something else, something similar but on the other side. So let's see what all these remarks mean. Okay, so the solution of course starts with this. Let G be a graph such that the minimum degree is at least 2 and the girth is greater than or equal to 2, greater than or equal to g, and that is a natural number. Now we have to prove this. Let small g be odd, then small g is equal to 2r plus 1 for some natural number r. Now what we will do is that we will start by assuming a central vertex in G, and this is how we also started in that result which comes before this definition, okay, where we have an upper bound for this. Let Z be a central vertex of G, and in fact this sentence is exactly what you will get in that proof. Di be the set of those vertices in G that are at distance I from Z. Okay, so they are I distance away from the central vertex Z. So there are some things that we can immediately conclude about D0. D0 is the set of those vertices by this definition that are at distance 0 from Z, and the only such vertex is Z itself. So that means D0 has size 1, it's a singleton set. And if you want to be more elaborate, you can mention that this is equal to the cardinality of the singleton set Z. And what can we say about the size of D1? D1 means you have Z here. D1 is precisely the set of all the neighbors of Z, because these vertices will precisely be at distance 1 from Z. So this is D1, this set. So the size of D1 actually is equal to the degree of Z. Okay, precisely it's equal to the degree of Z because that's what degree is, but that of course is greater than or equal to the minimum degree delta. So we can write this, since delta is the smallest possible degree of any vertex in G. Okay, now we are going to claim something. For any I line between 1 and r minus 1. We claim that the size of the I plus 1th set di plus 1 is greater than or equal to, for some reason I can't I don't know why, but I can't remember that the inequality should be like this. It always seems, why I don't know, that it should be less than or equal to this. And that of course is wrong. This is the actual claim. Okay. Now we need to establish this claim. You may remember that in the proof of that result, where we have an upper bound for the order of G, there also we claim a similar inequality, but it's in the other direction. So that's what I meant when I was saying that we are going to do something similar but in the other direction, on the other side. Now to establish this claim, let's do this. First of all, let's try to understand the situation by drawing a figure. And in the figure itself, we will establish our claim and then we will write. So the situation is like this. This is the central vertex Z, and we have the vertex di, which consists of those vertices that are at a distance I from Z. So we have some vertices here. After this di level, if you want, you can call this level I also. We have the level, the next level di plus 1, which according to distances from the central vertex Z is the it consists of those vertices that are one step further away from Z than the vertices in di are. Okay, so here also you have some vertices. So this is the I plus 1th level. Okay, now you concentrate on a vertex at the ith level. Say this is a vertex. Obviously, the distance from Z to this vertex is equal to I. If we name this vertex, say, we call it U. Okay, so the distance from Z to U is equal to I, and that distance is of course the length of some shortest path from Z to U by definition of distance. Okay, some path is there of minimum possible length that joins Z and U, and such that the length of this path is equal to I. Alright, and this path, if you think about it, this path will have a vertex at the I minus 1th level that is adjacent to U. Okay, alright, so that means U, the vertex U will have its own degree, which equals the number of edges that are coming and falling at U, number of edges incident on U. So already this edge is contributing 1 to that degree, but there are others also likely. So the thing here is that what about the other vertices? I mean that are and what about the other edges that are emanating from U? The claim here is that at least some edges are emanating from U which are taking us even further away from Z. That means these edges do not go back. But how many? We claim that actually, except this edge, this of course takes us back, all the other edges that are going to emanate from U, that means which are the edges that are going to contribute the rest of the degree to U, they will take us further away from Z. And that now we have to prove. Suppose that is not true. That means besides this edge, and in fact we can give it some name, say, oh well, actually I should have, it does not matter although, but still, let me just change it a little bit, okay. Let me call this one I plus 1, this one I plus 2, and this one I. Okay, so this is the ith level. There is no harm in calling this one di minus 1, this one di, and this one di plus 1. But I am, for some psychological reason, I am a little uncomfortable with I minus 1. Okay, so this is di plus 1 and di plus 2. So let's call this vertex V, the vertex that has that will take us from Z to U. On that path we have this V, and the next stage is U. So what we are saying that among all the edges that emanate at U, this is the only one that takes us back. That's what we want. That's what we want to be true. Suppose that is not the case. That means U will be adjacent to some other vertex in di at that in that set di. In fact, actually in general that need not be true. I mean, what we are now supposing is that no vertex from a lower level is adjacent to U. So that is not necessarily only in the set di, but all the lower levels. So now our supposition is this, that okay, U is adjacent to V, but say U is also adjacent to something else in the inner part of this diagram. That means this is precisely what we are supposing now, that U, let me call this vertex W. So is the figure clear? U is at the level di plus 1. Its immediate neighbor at the lower level di is V. But we are supposing that it has another neighbor at a lower level. And this other neighbor W may be here itself, at this level di. But this is precisely what we want to say. So this is an edge, it belongs to the edge set of G for some W belonging to a lower level set dj, where j varies from 0 to I, because the original U is at the level I plus 1. Okay, so suppose this is the thing. But at the same time, since we are considering the level di also, so there is a chance that this W may coincide with V. That's not what we are trying to suppose. So we subtract, we remove this V from this choice, so that even if W belongs to di, it is not equal to V. So now the situation is this. Let me draw a clearer picture here. This is Z, the central vertex. This is V. This is U. And U is adjacent to W. Alright. U is also adjacent to V, and there is a path of length I from Z to, the lengths will now change, from Z to V the length is I, from Z to U the length is I plus 1, and these two lengths are of course 1. Okay, and now there will of course be a path. Okay, watch this carefully. This W belongs to some dj here. For to be specific, suppose W belongs to dj for some j lying between 0 and I. So you will find by the definition of dj a path of length equal to j that joins Z and W, and you thus get a cycle. Okay, but there is a catch. These paths themselves may not give you a cycle. Why? Because these are single edges, fine, joining V and U and W and U, but the other parts are paths. There is a possibility that they may cross each other. Okay, so that this itself may not be a cycle, but there may be smaller cycles within this whole path. I mean, if you think of it as a path, it goes from here to W and then goes from W to U, from U to V, and then comes back to Z. If you think of this as a path, it's a closed path, and in that path or what, I am not really distinguishing between the technical terms, just we want the understanding. So in this path, if there are overlaps, then you will get some smaller cycle, but in the extreme case, this itself is the cycle. So that means in any case you are actually getting a cycle from this situation whose maximum length is the length of this cycle. But if you have some smaller cycles, then of course its length is even smaller. But what is the length of this? So from this situation, what you are getting is a cycle C. And why are you getting a cycle C? Because you start from Z and you come back to Z. If there is an overlap in between, then you start from somewhere and you come back to that itself, creating a cycle. In any situation, there is a smallest such coming back, and so you have a cycle. And its length is less than or equal to j plus I plus 2. J plus 1 plus 1 plus I. Alright. But what is j? Since j is coming from here, so j is less than or equal to I. That means this is less than or equal to 2i plus 2, or 2 times I plus 1. But now you see the range of I. I plus 1 is less than or equal to what? R. So this is less than or equal to 2R. So the length of your cycle, whatever you are getting from this situation, is less than or equal to 2R, which is strictly less than 2R plus 1. But 2R plus 1 is what? 2R plus 1 is G, because that's where we started the things, right? G is 2R plus 1, and the girth of the graph is greater than or equal to G. So that means this cycle will have length strictly less than, see, there is a strict inequality here. strictly less than the girth of G. And that is not possible because by definition the girth of G is the length of any smallest cycle in G. So that's why this supposition has led us to this contradiction. And that establishes what we were trying to say here, that whenever we are going outside from Z now, the situation is this. This is the only thing that is going to happen. You start at Z, then you go to D1. Okay, so these are vertices in D1. Alright, but then you go further away from Z, then you will have some other edges emanating from this D1 level vertices. So what is going to happen is that this is the only way of going out. Okay, there is no coming back from any other way by what we have done just now, and they themselves will further take you further away, further outside from Z, and this also will not come back. I mean, none of these things is going to take you back. So it's like a chain reaction, right? But then from this fact we have this. Why? Because if you think of it, what is the size of Di? This. Okay. And so that means there are that many vertices in Di. Now each vertex is giving rise to some further vertices, and those further vertices will contribute to the size of Di plus 1 because they make up Di plus 1. Alright. Now say this is your Di, just for the sake of argument, say this is your Di. This vertex is giving rise to some other vertices. This one is giving rise to some other vertices. At least how many new edges are being given rise to? The minimum degree that any vertex has is delta. It's actually greater than or equal to delta, but this is the minimum possible. Now from that, if you subtract one edge, because that is not going to contribute to Di plus 1, then you get delta minus 1. At least that many edges are emanating from each vertex at the level Di. That will give you further vertices in Di plus 1. So you multiply this number by the number of vertices Di has. So that many vertices will be there in Di plus 1 at least. Okay, at least means actually it will be equal, I think. But we don't of course need equality. Inequality is enough. So that's how we have this inequality. Now let's write these things. Now that we understand what we are going to write, now if I write systematically, you won't have any difficulty understanding. Let oh, I forgot which one. Yeah, I think I started by considering U. Let U belonging to Di be any vertex. Suppose UV. Oh, okay. Okay. Yeah. I think I have already made a mistake. U has been chosen in Di plus 1, not Di. I think I messed up. Okay, let me just see. Let me write this thing from here and then I will come back to this. Let U belong to Di plus 1 be any vertex. let V belong to di such that uv is an edge in G. Now suppose uw is an edge in G for some vertex w belonging to the union of all the, this is J, all the dj's where j varies from 0 to I, and from where we are of course removing v so that this w doesn't coincide with v. Then you see how directly we are going to bypass all those things, all those explanations, and simply write then G has a cycle of length L such that L is less than or equal to j plus I plus 2, but then which is less than or equal to 2i plus 2, because j is at most I, that is equal to 2 times I plus 1, but I plus 1 is less than or equal to R. Okay, and this is equal to G. It's really amazing to think that people come up with these things. Someone came up with these things for the first time. I'm talking about their original result, that this n naught of d comma g, that thing. Okay, so we have found a cycle of length L that is less than the girth. This is a contradiction and proves that no such vertex W exists. Hence, okay, so I was saying there that I messed up a little, no? The original inequality is this. Am I getting this from what I have written here? I mean, my confusion is about I and I plus 1. Well, actually, ultimately it does not matter, since if in place of I you write I plus 1 and here I plus 2, that does not matter. The fact is that the ith level, whatever I is, gives rise to at least this many vertices at the I plus 1 level. Instead of writing this directly, shall I write one more line? So, each vertex in di corresponds to at least delta minus 1 vertices in di plus 1. But after writing this line, you may have another doubt. Can we have something like this? Say this is a vertex in di, this is another vertex in di. This one is contributing delta minus 1 vertices, and this one is also contributing delta minus 1 vertices, but we have common contribution. If that happens, then of course we cannot directly write that inequality. However, this cannot happen, because if this happens now, then already we are getting that contradicting situation. Because if you are at the level di plus 1, we have already proven that only one vertex can go, only one edge can go back, not more than one. Okay, so whatever we proved here, whatever we argued for here, already takes into account this situation. So, man, there are so many things in this even small space. So, now finally we can write this. From this, we are going to get, if you keep using this repeatedly, then you are going to get everything in terms of, this is a formula that can be repeatedly used to reduce, right? And you ultimately get this. Less than or greater than or equal to delta times delta minus 1 to the power I. Hence, and now finally we go to the order of G. You see, every vertex is after all at some distance away from the central vertex Z. So if you take the union of all the di's, you are going to get the entire vertex set of G, varying the value of I, of course. I will start from 0 because we have to take into account the central vertex Z itself, and I will stop at R. Why, that I leave to you to figure out. Hence, this is equal to 1 plus summation of this. Do you understand where this 1 is coming from? This is the size of D0 plus the sizes of the other di's. And by the way, how are we able to just simply take sum? That's because the di's are mutually disjoint. They cannot intersect. A vertex which is at distance I from Z cannot be, say, at distance I plus 1 also at the same time, or some other I value. So that's why the union is disjoint, so its size is the sum of the sizes of the sets. Now you can change the suffix a little bit so that it comes in the form of that original in not that definition. So in place of I, we are writing I plus 1. So here we have to subtract from the limits in order to keep the sum same. And now this is less than or equal to 1 plus, so you use this inequality, delta can be taken common out, and this is nothing but this. And that is the case when G is odd. And now you have to similarly figure out the case when G is even. That part is left to you. It may seem daunting at first, but once you see this solution 2 or 3 times, you will get the idea. There will be some minor differences only in that even case from this case. So that's where I am just ending, and tomorrow we have our upload again, of course, and tomorrow let's solve group theory problems from Gallian. So with that, see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.